Chromatography is based upon the distribution, or partition, of analytes between the mobile phase and the stationary phase. The equilibrium of analytes between two different phases, referred to as Kd, is represented by the equation. This takes into account the concentration of the analyte bound to the stationary phase, and the concentration of the same analyte traveling in the mobile phase. It is similar to the idea of liquid-liquid extraction, where an analyte will partition between an aqueous and organic layer to the same degree, provided all other variables, such as temperature, agitation time, and pH, are constant. The difference with liquid chromatography is that one layer is moving. For reverse phase, RP, HPLC, the organic layer is equivalent to the column stationary phase, C18 for example, and the more polar mobile phase is part of a dynamic system. The continuous flow of mobile phase in HPLC means that when analytes bound to the stationary phase enter the mobile phase, they are transported along the column. The movement of the mobile phase in a definite direction, driven by the pumps, therefore means that an equilibrium is never reached. There is instead a continuous dynamic with some proportion of analytes interacting with the stationary phase and the remaining analytes of the same type moving through the column in the mobile phase. This movement of analytes away from those in the stationary phase disrupts the Kd equilibrium, causing the analytes in the stationary phase to re-enter the mobile phase, which again disrupts the equilibrium, so some analytes then re-enter the stationary phase. This is how analytes travel through the column. If there are strong interactions with the stationary phase, and not much affinity for the mobile phase, the analyte will have a high Kd value, and will take longer to move through the column. It will be immobile, interacting with the stationary phase, not progressing through the column. If there are only weak interactions and the analyte prefers to be in the mobile phase, then movement through the column will be much faster. This gives a low Kd value. In chromatography, the principle, like dissolves like, applies, meaning nonpolar analytes interact well with nonpolar stationary phases, leading to higher distribution constant, Kd, values and improved separations. Neutral or ion-suppressed analytes, being more nonpolar than ionized ones, exhibit enhanced retention on nonpolar reversed phase, RP, stationary phases. The pH of the mobile phase significantly affects the ionization state of ionizable analytes, necessitating buffer usage to maintain the analyte in the desired state. At a pH equal to its P.K.A, an analyte exists in both ionized and neutral states, resulting in multiple K.D values and poor chromatography with broad, tailing peaks. Acidic analytes in acidic environments, pH at least 2 units below their P.K.A, retain their protons, leading to ion suppression and improved retention on HPLC. In more basic environments, acidic analytes dissociate into their conjugate base, becoming ionized and resulting in reduced retention on HPLC. Basic analytes in basic environments, pH at least 2 units above their P.K.A, remain in their ion-suppressed, neutral form, improving retention on HPLC. In more acidic environments, basic analytes become protonated and ionized, leading to reduced retention and earlier elution on HPLC. The pH also affects the column stationary phase, with very low pH causing stripping of the bonded stationary phase, high pH damaging the silica support, and mid-pH ranges causing ionization of silanol groups, increasing tailing observed with analytes containing basic functional groups. Any compound containing acidic and/or basic functionality has a specific ionization constant, or Ka, which indicates the degree that the acidic or basic moieties will ionize in an aqueous solution. If an analyte is readily ionizable, it will have a large influence on the concentration of H+ in the solution. The greater the ionization, the stronger the acid or base. The pKa is the logarithmic acid dissociation constant and is the commonly used form of this ionization constant. If an acidic analyte has a high pKa, it is less likely to ionize or dissociate and so is a weak acid, typically with pKa values between 2 and 12 in water. If a basic analyte has a high pKa, however, this analyte is more likely to ionize and so is a strong base. It is important to note that it is not possible to discern if an analyte is basic or acidic by its pKa. Very weak acids will have high pKa values. It is the functional groups that determine the acidity/basicity of a compound. The reason the pKa of your analytes is so important in HPLC is because when the pH is set close to the pKa, the analytes will be present in solution in both neutral and ionized forms. Those in the neutral, nonpolar, form will be well retained by the nonpolar Rp stationary phase. But those in the ionized state will have less retention, a different Kd. Therefore, all analytes of the same type will not be traveling through the column in the same manner, resulting in very poor peak shapes and irreproducible chromatography. A good rule of thumb is to fix the pH for an acidic compound at least 2 pH units below the pKa, and for a basic compound it should be set at 2 pH units above the pKa. This ensures that the pH is far enough away from the pKa that any small changes in mobile phase pH will not have a dramatic effect on analyte retention and peak shapes. As can be seen using the diagram showed for acetic acid. The ideal pH for a mobile phase sits within the plateau region for the neutral form of the analyte. It is important to point out that it may not be as simple to follow the 2 pH units rule when working with bases that have pKa values above 8. If the rule is followed, the pH of the mobile phase would need to be at pH more than 10, which is outside of the working pH range of most silica columns. Similarly, if an acidic analyte has a pKa of 3, a mobile phase of pH may first well be too low for the column. These two extremes of pH cause different effects, but both are equally as damaging to standard silica-based columns. At high pH, the silica support inside the column will be damaged due to dissolution of the siloxane bridges in the silica backbone. The silica will start to fall apart. At low pH, the bonds holding the stationary phase onto the silica support will be cleaved, resulting in loss of chromatographic performance. In the case of weak bases, the first option relies on exploiting any additional hydrophobic interactions between the analyte and the Rp stationary phase to maintain sufficient retention. If the basic moiety is part of a large nonpolar molecule, it may be possible to analyze it at a low pH, in the ionized state. The hydrophobic interactions should overcome enough of the polarity introduced by the protonation of the base to ensure adequate retention. The added benefit of analyzing bases at low pH is the ion silanol groups, SiOH, on the silica support will be ion suppressed. At a pH above their pKa, about pH 4, ion silanol groups act like an acid and will dissociate to give ionized SiO that interacts strongly with basic moieties and results in bad peak tailing. At low pH, the SiOH remains neutral. If the additional hydrophobic interactions do not provide sufficient retention for the analyte, one alternative would be to use a polar embedded, or polar end-capped column. These columns have polar groups within, or end-capped onto the silica backbone of the column, and so allow very highly aqueous, 100%, mobile phases to be used without the risk of phase collapse, self-association. The highly polar, ionized bases are more likely to be retained by the increased polarity provided by these more polar Rp stationary phases. The second option for working at extremes of pH requires the use of specialized columns, such as Agilent's Zorbax Extend or Zorbax Stable Bond, that incorporate additional chemistries into the stationary phase to protect the silica and/or the bond retaining the stationary phase. It is important to note that while these columns can be used at extremes of pH, it is never advisable to store columns at these extremes. The final option is particularly relevant to analysis of samples containing mixes of weak acids and bases where at least one functional group will be ionized at whatever pH is chosen. Or analysis of strong acids and bases, or analytes that have multiple functional groups. In cases such as these, the pH of the mobile phase is used to fix the relevant analytes in the ionized state, so that they will interact ion pair with a modifier added to the mobile phase that carries the opposite charge. This interaction leads to an overall neutral molecule that will then be successfully retained by a HPLC column. If you use trifluoroacetic acid, TFA, in your mobile phases, it lowers the pH to ion suppress any acids, while also ion pairing with any ionized bases. Other common ion pair reagents are quaternary ammonium compounds, for example tetrabutylammonium phosphate, to ion pair with acids and suppress weak bases, and alkyl sulfonic acids to ion pair with bases and suppress weak acids. Triethylamine, TEA, is another commonly used modifier, often referred to as a sacrificial base that will ion pair with ionized silanol groups on the stationary phase, reducing peak tailing effects. A disadvantage of using ion pair reagents is that you are chemically modifying your stationary phase and so should always have ion pair dedicated columns. This ensures that analyses not requiring ion pairing are not affected by this change in column chemistry. Also, very high concentrations of ion pair reagent can result in any neutral analytes present in the sample having limited access to stationary phase, resulting in decreased retention. Some ion pair reagent also have significant UV activity, and so may absorb light at the analytical wavelengths being used with UV detection. For example, the UV cutoff for TFA is 210 nanometer.